Kia ora, Year 12 and 13. Here's question 3B from last year's scholarship calculus paper. It's got a bit of differentiation and a bit of integration. Okay, so it starts off with the integration by parts formula. Now, some of you watching this will know how to do integration by parts, and if you do, that's a bonus. But all you've got to do really is carefully apply the formula. You'll be more comfortable if you've done it before, but the big idea is that we're going to split our integrand, the thing in here, into two bits. One bit and another bit. And we look for one that is easy to integrate, and we're going to leave the other one alone. So I'm going to come back to how we do that when we get into the question. But basically, when you get to that part of the question, you can come back and plug through the formula. The question starts here. We've got a curve passing through a point, and it's got the property that everywhere on the curve, the gradient is this. So we've been given a little differential equation. dy by dx is equal to x minus 2y. It's a two-part question. The first part is a show that question. Show that the derivative of e to the 2xy is equal to this thing. And then from there, we're going to find the equation of the curve. So somewhere in that problem, it's going to be very useful that we know dy by dx. If you look at part 1, if you want to differentiate something with x's and y's mixed up, think about what you use. Pause the video and have a go at getting through the first part, and I'll do it on the next slide. Okay, so we've got to find this derivative. And we're going to use implicit differentiation to do that, and the product and chain rules mixed in. So it's going to equal the first function, e to the 2x, times the derivative of the second, dy by dx, plus the second function, y, times 2e to the 2x. Now we know that dy by dx is equal to x minus 2y from the question, so we're going to substitute that in. Expanding that out, we get x e to the 2x minus 2y e to the 2x plus 2y e to the 2x, which equals x e to the 2x as required. So the next part of the question tells us, hence or otherwise, find the equation of the curve. So let's write down what we know. Well, we've got from the last bit. We know that the derivative of e to the 2xy is equal to this thing here, which has just got x's in it. So our goal is to end up with y equals something. We want the equation of the curve. We've already used the fact that the gradient along the curve is this. I think it was x minus 2y. Right, so that bit of information probably we're not going to use directly in here because we've already used it in here. But we know that if we differentiate this, e to the 2xy, we end up with this. So we can integrate both sides. So if we anti-differentiate e to the 2x x dx, that's going to get me back not to y, but to something like y. So we might try that as a first step, and then we can hopefully figure out what c is and manipulate that to end up with y equals. And it turns out that all we have to do is to do integration by parts. So integration by parts goes like this. I'm going to choose one of the two things to integrate and one to leave. Now I'm going to integrate this one, and I'm either going to leave or differentiate this one. Right, if you write down the formula from the first slide, you can see what I'm doing with the F's and G's. I'm not going to use that notation directly, I'm just going to get on and do it. So this is what we've got here. So the first part of integration by parts is to say leave the one you're going to leave, so that's the x, and integrate the other one. And we get half e to the 2x. Right, so that was easy. Now we're going to subtract the integral of 1, so that's the derivative of this one, 1 times, and again we integrate the e to the 2x dx. Right, now if you've got this far you should be feeling pretty happy because that second integral is really easy. So here I've got x on 2 e to the 2x. Now integrating this, it's just backwards chain rule by inspection. So it's going to be e to the 2x times 1/4, right? Because when I differentiate, I pull down that 2, so I need to have a half times a half. If you're watching this, you're probably pretty comfortable with that. If you're not, you need to go into delta and do some more practice on backwards chain rule. So that's what I've got to. Now that's really good because now I can see that I'm getting very close to having e to the 2xy. In fact, we're just going to write this in here. So that's where I've got to. We're going to need one more slide because we now have to use the specific information to figure out the plus c, and then we've got to get y equals. Alright, so starting from here again, e to the 2xy equals x on 2, e to the 2x, minus 1/4, e to the 2x, plus c. But we know that 1, 1 is on the curve. So we're going to substitute that in. We get e squared times 1 is equal to 1/2 e squared minus 1/4 e squared plus c. So e squared equals 1/4 e squared plus c. C is equal to 3/4 e squared. Now for heaven's sake, do not take out your graphics calculator and calculate that as an approximation, right? Just leave it sitting there like that. One more slide to finish off. So now we have e to the 2xy is equal to x over 2 e to the 2x minus 1/4 e to the 2x plus 3/4 e squared, and we're going to divide all of that through by e to the 2x, which is the same as multiplying by e to the negative 2x, so you could do either of those things. I'm not sure whether they'd give you full marks for this question, but we're getting fairly close to it now. So looking at that, I'm going to clean that up just because I've got time. I'm not sure if I were in the exam I might stop at that last line. So here we've got x on 2 minus 1/4 plus 3/4 e to the power of 2 minus 2x. So that's the equation of my curve, and I think that deserves a happy face. Alright, thanks for watching. Please let me know if you're out there watching or if this is any use. If it is, I might keep going and do some more.